Alright, my name is Nelson Sasona,
I'm Christian.
and we're doing our presentation on students' t-distribution and their mechanics, basically just t-curves. Alright, so the topics that we will be going over in our presentation include history of t-curves, the relation to normal curves and how they differ from normal curves, when to use a t-curve, t-curve mechanics, going into detail about degrees of freedom, and finally real-life applications. History of t-curves. T-curves were invented in the very early 1900s by an engineer who worked at a brewing company in Ireland. This charming young man here was that man, and his name is William Seeley Gossett. He was quite an intelligent individual, and he was gifted with the knowledge of statistics. Gossett applied this knowledge to his everyday life, especially at his job on the brewery. He was in charge of testing the quality of the alcohol the brewery was producing, and he also rejected the alcohol that didn't meet standards. And because of the dangers of drinking an abundant amount of alcohol, he was forced to use smaller samples. But what he noticed was that when he used a small sample, the tests that he used weren't exactly normal. He knew this because when he sent back samples that he rejected, they were actually perfectly fine and were met standards. He ended rejecting 3 times as much alcohol as he should have been, and this was caused by the increased variability due to having smaller samples. According to a normal model, you should only be rejecting maybe 5% of alcohol that's actually okay and is perfectly fine, but he ended up rejecting 15% of alcohol. Gossett was annoyed by the fact that something was wrong with his model, and this caused him to create a new type of model that accounted for the increase in variability, which he called a t-distribution. Unfortunately, the brewing company had policies against publishing industrial secrets, so Gossett had to publish his work under a pseudonym known as Student.
Relations of t-curves to normal curves. T-curves or t-distributions are very similar to normal curves or normal distributions in that they are unimodal, symmetrical, and bell-shaped. The main objective of t-curves is to compensate for the increased amounts of variability due to having smaller sample sizes. Because of this, as shown in figure 1, the distribution of t-curves shown by the solid line is shorter than the distribution of the normal curve, shown by the dotted line. The question is, what do we consider a smaller sized sample? Fortunately, one of the attributes of t-curves is that they can compensate different amounts depending on the actual size of the sample with a parameter known as the degrees of freedom. Degrees of freedom attained by the equation n-1, where n is the sample size, determines the amount that the t-curve is spread in comparison to the normal size. Essentially, as shown in figure 2, the smaller the sample size and coordinating degrees of freedom, the wider the curve is. The larger the sample size and coordinating degrees of freedom, the less the t-curve is spread and the closer it is to becoming a normal curve. Because of this, the larger the sample size, the more normal it becomes. Theoretically, because of this, a t-curve would be normal when with a degree of freedom of infinity. This follows the central limit theorem.
When to use a t-distribution. In general, t-distributions are used with small sample sizes, and you are also never given the standard deviation. A general rule that people use is that, well, with small sample sizes that is that if the standard deviation is not known, then you should use a t-distribution. And if the standard deviation is known, then you should use a normal distribution. However, if you do not have a standard deviation, but the sample size is large, then you should probably just use a normal distribution. Another rule that people often use is a rule based on sample size. Usually, if the sample size is less than 30, we use a t-distribution. And if it is greater than 30, we use a normal distribution. We can do this thanks to the central limit theorem. This theorem basically just states that if we take a large enough sample, the distribution of the sampling means will be normal, and it doesn't matter what the shape of the original distribution was.
T-curve mechanics. The mechanics of T-curves are incredibly similar to those of normal curves. The main deviation between the two is the degrees of freedom. Recall that to obtain critical points from a normal curve, we selected inverse norm on our calculators, then entered the percentile rank for this desired point. For example, when using alpha levels on a hypothesis test, we used 0.995 for 0.01, 0.975 for a 5% alpha level, and 0.95 for 10% alpha level. Obtaining the critical points from a t-curve is very similar. We select inverse t instead of inverse norm and enter one of the percentile ranks, the same ones that we would have entered for inverse norm. The main difference, however, is the fact that we enter the degrees of freedom, which, as stated before, comes from n-1, where n equals the sample size, with the degree of freedom after the comma before pressing enter. Like obtaining the critical points, the mechanics for obtaining the probability from the t-score is very similar to those of the normal models. However, like obtaining the critical points, there are slight differences. Recall that to obtain the probability for a z-score on a normal curve, we selected normal CDF, then entered the bottom z-score and top z-score, which we would have done negative 99 to that point, or that point to 99. To obtain the probability of a certain t-score on a t-distribution, we selected normal TCDF, then we also entered the bottom and top t-scores. However, like obtaining the critical points, we also entered the degrees of freedom after entering the column.
More on the degrees of freedom. The equation for degrees of freedom seemed really random, didn't it? It was only n-1. But there's an underlying reason behind all this madness. The reason comes from the general theme of t-curves, which is compensation. The equation for the true population standard deviation is shown here in figure 1. The standard deviation is equal to the square root of the summation of each of the data points minus the population mean squared over n, which is the sample size. However, we do not know the population mean or the value of each datum in the population, so therefore we are forced to use the sample mean and the datum in the sample, which is shown here in figure 2. However, this causes a problem. Because the sample mean is the mean of the sample datum, and yes, we are being redundant, generally speaking, the datum will be much closer to the sample mean than the population mean, assuming the population mean and the sample mean are not equal. This creates a problem, because the difference between the sample datum and the sample mean is smaller than the difference between the sample datum and the true population mean. The summation of the squares of the previous will be smaller than the summation of the squares of the latter. In order to compensate for this, we divide the summation by n-1 instead of n, essentially fixing the smaller summation value by dividing it by a smaller value. Real-life applications. Compared to normal curves, t-distributions are much more accurate, being able to compensate for the natural variability. Because of this, in any real-life situation where statistics are necessary, such as building confidence intervals or conducting hypothesis tests, one can be more accurate. Though if a wealthy corporation wishes to spend millions of dollars to conduct surveys, it would obtain fairly accurate results with a normal model. One could obtain similarly accurate results with a t-distribution. In addition, when one is only able to obtain a small sample size, like the discoverer of the t-distribution, Gosset, one can obtain much more accurate estimates with the t-distribution. And now Curtis will give you guys a step-by-step run-through of this sample problem right here.
We have just gone over real-life applications for t-curves. Here is a scenario in which t-curves are used to solve a real-life problem. Let's say a nutrition laboratory tests 40 reduced sodium hot dogs, finding that the mean sodium content is 310 milligrams with a standard deviation of 36 milligrams. Find a 95% confidence interval for the mean sodium content of this brand of hot dog. Well, first, because it's a confidence interval, we write out the equation for a confidence interval, which is y bar equals y bar plus or minus me, where y bar equals 310 and m is the t critical points, E is a standard error. In addition, the number equals 40, giving us a degree of freedom of 40 minus 1, or 39. Standard deviation is also given. The standard deviation of the sample mean, is given at 36. First, we can find m using inverse t. We enter inverse t 0.975, the coordinating percentile rank for 5%, and the degree of freedom of 39, which gives us (2.022690901). We then find the standard error, which is given by the equation n, where the standard deviation equals 36 over the number, which equals 40. This gives us 5.692099782. We then plug in these values into the original equation up here. So 310 plus or minus 2.022690901 times 5.692099782. We then put this into notations that people can actually understand. Using the calculator. From this, we conclude that the true mean sodium content of this brand of hot dog is in between 298.4866416 and 321.5133584.